My name is Puya Taghavi, and I will be discussing some of our work here at the agency to estimate CO2 emissions. The IEA's CO2 emissions from fuel combustion publication provides emission estimates for all the countries and regions covered by the IEA statistics, and has become an essential tool for analysts and policymakers across the international fora in the recent years. We'll have a brief introduction to greenhouse gases and global warming. We'll have a look on why energy data is key for understanding the emission trends and tackling our climate issues. Then we'll have a look of the scope, which is covered by the IEA CO2 emission estimates, and the methodology used here at the agency to estimate CO2 emissions. And finally, we'll briefly look at some of the efforts here at the Energy Data Center to enhance the coherence of energy data for a climate agenda. So without further ado, I'm just going to start the presentation with the introduction to greenhouse gases and global warming. Perhaps some of you are already familiar with the concept of greenhouse effect. CO2 alongside methane, N2O, fluorinated gases, water vapor are among the greenhouse gases. And the greenhouse effect corresponds to the circumstances where the short wavelengths of the sun radiation can pass through these gas molecules and reach the Earth's surface. However, the re-radiation from the Earth's surface, which corresponds to higher wavelengths, is partially absorbed by these gas molecules in the atmosphere. And what has happened is that in the recent years and with the anthropogenic or human-induced activities, the concentration of the greenhouse gases in the atmosphere have been substantially increased. This is more dominant for CO2, which had a concentration around 288 ppm in pre-industrial levels and has reached a concentration around 414 ppm today. And we're on our way to doubling this amount by the end of the century. So because of this increase in the concentration, there is more trapping of these re-radiations happening in the atmosphere. And this has resulted in an increase in the global mean surface temperature, which we know as global warming. And it's important to note that the combustion of fossil fuel is the main source of anthropogenic CO2 emissions. So again, today it's the scientific consensus globally that the anthropogenic activities have resulted in this increase in the global mean surface temperature. This is a graph from the IPCC special report on global warming of 1.5 degrees C. And you can see different pathways, but what's important is that the global mean surface temperature can increase up to 5 degrees C comparing to pre-industrial levels if the current trends are continued, that no significant action is taken. Let's have a look at some of the international efforts so far to address the climate issue. I'm going to start by introducing the United Nations Framework Convention on Climate Change, the UNFCCC, which is an international treaty adopted in 1992 in order to help address climate change. Since 1995, the parties to the conventions have met annually in a conference of the parties, or COP, to discuss their progress towards reducing their climate impacts. It was in 1997 which the Kyoto Protocol was adopted, setting legally binding obligations for the developed countries to reduce their emissions. And it was in the 21st Conference of the Parties, or the COP21, which the famous Paris Agreement came into effect, with the aim to limit the global average temperature increase to well below 2 degrees C, with efforts to limit this temperature increase to 1.5 degrees C comparing to the pre-industrial levels. Paris Agreement actually came into force in 2016, and more than 190 countries globally have ratified it. And this year especially, it's very important in our international efforts to tackle climate, because we've come out of a pandemic And there is the COP26 or the 26th conference of the party, which is scheduled to be held later this year in November in Glasgow. And with the current ambitious announcement by governments around the world for net zero emission targets, this year has become very important. And as a result, IEA is also helping to build on the momentum necessary before the COP26. We're having a net zero summit at the end of the March 31st, which we will be co-hosting with the COP26 Secretary, the UK government. And the plan is to bring global leaders representing the majority of the global GDP to discuss and have a dialogue of how the countries can accelerate the transition towards low carbon energy technologies and reduce their emissions. And on top of that, IEA is planning to publish the first global roadmap to net zero emissions by 2015, early summer in May. And this is a photo of our executive director and the COP26 secretary, Mr. Sharma, which are hanging out while they're having social distancing measures in place. So let's have a look of why energy data are key for understanding the emission trends. Credible and validated energy data are essential for having estimates which can be trusted. And estimates which can be trusted can provide insightful input into the climate and energy policy making agenda. So the comprehensive energy data will enable us to understand the key fuels and sectors which drive the emission trends. As you can see on the graph on the left, this is the CO2 emissions from fuel combustion globally from year 1971 to 2018. And as we can see clearly from the trend, the emissions have actually been more than doubled in this period. And what we can see on the right figure is the sectoral CO2 emissions from fuel combustion. The power generation, so the electricity and heat generation, correspond to about 40% of the global CO2 emissions. However, disaggregated energy data enables us to allocate the power generation emissions to the end sectors, and as such have a better understanding of the real drivers of CO2 emissions. This is evident on the column on the right. And as you can see, after such allocation to the end sectors, transport and industry together correspond to about 70% of the global CO2 emissions from fuel combustion. Again, comprehensive data enables us to populate metrics which can help us to understand the macroeconomic drivers of emissions. The formula on the top right, it's called the Kaya identity, which provides a decomposition of CO2 emissions into 4 macroeconomic factors. These are the population, the GDP per population, the total energy supply per GDP, which is essentially the energy intensity of the economy, and CO2 per total energy supply, which is the carbon intensity of the energy supply mix. And if you look at the figure, globally and in the past 20 years or so, so starting year 2000, we can see that the increase in the GDP per population, which you can see it's the green line, alongside the increase in the population, the blue line, have been the main factors driving the CO2 emission trends upwards, while they have been slightly offset by the decrease in the energy intensity of the economy. This is the yellow line on the graph. And it's also interesting to see that the carbon intensity of the energy mix, which is the red line on the graph, has stayed relatively flat for the past 20 years. This represents the continuous dominance of fossil fuels in the global energy supply mix and the low and slow uptake of the low carbon energy sources, despite the current efforts globally for decarbonizing the energy sector. Now we can have a first quiz, so you guys can also participate and cast your vote in. It's a Menti question. What percentage of the global CO2 emissions from fuel combustion in 2018 comes from coal generation? So we can have a quick detour to Menti. The code is on top, and you guys can participate and cast your votes in. So I see that so far, most of the guesses are around 45%. Some 55 and 135% so far. I'll give another few seconds for anyone else who wants to participate, and then we can have a look at the answer together. And yeah, I think it's a good time to now have a look at the answer, which is, yeah, as most of you correctly guessed, 45% of the global CO2 emissions in 2018 came from coal combustion. And it's interesting to look at that because despite the current efforts, especially in developing countries, to phase out coal generation, we can see that there's still a good majority of the emissions which is originated from coal combustion. Now back to the presentation, and let's have a look at the scope which is covered by the IEA CO2 emission estimates. The IPCC, with the help of IEA, have populated and refined a globally recognized set of guidelines for estimating and reporting greenhouse gases. The guidelines is called the 2006 IPCC Guidelines for National Greenhouse Gas Inventories. And this guideline is actually used by the countries in order to submit their national greenhouse gas inventories to UNFCCC. According to these guidelines, the countries need to report their emissions into 5 various categories, as you can see listed on the slide, which is the energy category, the industrial processes and product use, agriculture, forestry, and other land use, waste, and other. I want to emphasize that the IEA CO2 emission estimates correspond to category 1, which is energy-related emissions only. And if we have a more deep look, the energy sector is divided into 3 subcategories. And the IEA estimates actually cover category 1A, which is the emissions associated with fuel combustion activities only. So other energy-related emissions, such as the fugitive emissions, are excluded from these estimates. However, as you can see on the graph, the coverage of the CO2 emissions from fuel combustion corresponds to over 65% of the global greenhouse gas emission. And this highlights the fact that understanding correct reporting and trying to tackle these emissions, it's core and very important in our efforts to tackle climate change. So the boundaries of the IEA CO2 emission estimates can essentially be described by 2 words: energy and combustion. Again, the IEA includes the energy-related emissions only. There might be many hydrocarbons which are used for non-energy purposes, for example, as petrochemical feedstocks, solvents, and lubricants. And in many cases, the carbon included in the hydrocarbon might be oxidized and emit CO2. However, such emissions are excluded from the IEA estimates. And secondly, again, as we saw, we only cover combustion emission. And as such, fugitive emissions such as venting and flaring and losses due to distribution and transformation are excluded from the estimates that we provide. And another important fact is that the estimates that we provide are a bottom-up approach. It's a demand-side estimate, very similar to the sectoral approach included in the IPCC guidelines. And as such, we sum up the emissions across the total final consumption sectors, the electricity and heat production input, and the energy industry zone use to come up with the national totals. Another important principle is that the IEA emission estimates follow the territorial principle. And that means that in a nutshell, if it's a good or services which is produced in a country, and then it can be exported and used in another country, the emissions are accounted for where that good and service is being produced and not the final consumer. So for example, if some electricity is being produced in France and then exported and used in Germany, the emissions for that electricity generated are accounted under the France emissions. Or if there's some goods and services which are produced in China and then they're exported and used in Argentina, for example, the emissions are associated and accounted for under the Chinese emission. And this principle actually follows the guidelines for reporting national greenhouse gas inventories to UNFCCC. Another Menti question for you guys. So the top 5 emitters, which include China, US, India, Russia, and Japan, accounted for what share of the global CO2 emissions from fuel combustion in 2018? Another fast Menti detour for you guys to participate in this question.
Eight 211393 88211393 88211393, I think.
Yes, the code is 88211393. Okay, let's have a look at the answer. And as most of you guys have correctly guessed, it's about 60% of the global CO2 emissions. So it's interesting to see that only 5 countries correspond to this large portion of the global CO2 emissions from fuel combustion. Back to the slides. So now let's have a look at the methodology used here at the IEA to estimate CO2 emissions.
What is that?
Throughout our process to estimate CO2 emissions, we use internationally recognized guidelines and methodologies. So our process starts with collecting the underlying energy data in physical units through the national statistic offices and energy ministries in the form of energy statistics, which you guys have been already introduced to by my colleagues in previous days. And then from there, with the help of the calorific values and the international recommendations of energy statistics, we convert the physical units into energy units and form the IEA energy balances, which again, you've also already been introduced to. And finally, with the help of the 2006 IPCC guidelines and the default emission factors provided in the guideline, we estimate the CO2 emissions from fuel combustion. And I want to emphasize that this IEA estimates are a global benchmark based on harmonized definitions and methodologies. However, they do not provide the official source for national greenhouse gas inventory submissions to UNFCCC. To look in detail in how the emission estimates are done, we use the Tier 1 methodology from the IPCC guidelines, which is the most simple method provided in the guidelines to estimate CO2 emissions. And the main concept behind this method is that we have the fuel-specific activity data in energy units, and we multiply that by the fuel-specific emission factor provided in kilogram of CO2 per energy unit provided in the IPCC guidelines, and then simply we sum over all the sectors and all the fuels to come up with the country totals. And it's important to note that this tier 1 method follows a carbon conservation principle. And that means that all the carbon contained in the fuel is considered to be oxidized and emitting CO2. Again, this is a demand side estimate. So we sum up all the total final consumption sectors plus the input to electricity and heat production and the energy industry's own use to come up with the national totals. So in order to look into the methodology in a more detailed manner, we can divide it into two main steps. The first step would be to convert the mass units into energy units. For this, we simply need the calorific values. And I want to say that actually the tier 1 methodology allows using the default calorific values provided in the guidelines, as you can see on the right-hand side table. However, as we know, for various fuels around the world, they have various qualities and the calorific values might vary a lot. And as such, IEA tries to use time-specific, time-varying, country-specific calorific values. And we only use these default calorific values when there's no other data available. And as you can see on the table on the left, you can easily put the fuel activity data in mass units in column A, the calorific values in column B, and column C is a simple multiplication of column A and B, which provides the fuel consumption data in energy units. This is the first step. The second step is to convert the energy units into emissions. And again, this is simply done by multiplying the energy consumption by the default emission factors provided in the guidelines. You can see these fuel-specific default factors in the table on the right. And you can input them in column D, and column E would be just a simple multiplication and a unit conversion to have the CO2 emissions from combustion of each fuel. And at the end, you just sum over all fuels and all the sectors to come up with the country totals. So now that we looked at this methodology, it's good to have another Menti for you guys to get your hands dirty and try to have a little calculation here. So the question is, a car consumes 6 kilograms of motor gasoline per 100-kilometer trip. How many tons of CO2 is emitted after a 4,000-kilometer trip completed by the car? You have the calorific value as well as the emission factor for motor gasoline provided. So let's have another quick Menti detour. So you guys can cast your votes in. I'll give a little bit more time this time since there's some calculation involved. So take your time, take your pen and pencil. We have the consumption of the car. We know how long has the trip been, and then we have the calorific value and the emission factor. And we want to know how much tons of CO2 has been emitted. It's good that we have so far around 17 answers in. We'll give another 10, 15 seconds or so, and then we can actually have a look at the answer together. Okay, I think it's not a bad time to start looking at the answer. So the first step would be to have the activity data in physical units. So we know that the car is consuming 6 kilograms of gasoline per 100 kilometers, and the car trip has actually been 4,000 kilometers. So a multiplication will give us the consumption of gasoline in physical units, which is 240 kilograms. The second step would be to convert these physical units into energy units. And that is simply done with the help of the calorific value provided, which is 44.3 megajoule per kilogram of gasoline. And we get the activity data in energy units in this step. The next step would be to convert that into mass of CO2 with the help of the emission factor provided. And that's just another multiplication, and we have the result in kilogram of CO2. And then the last step is just the unit conversion, because the question was asking how much tons of CO2 have been emitted. So as you can see, this is as simple as what essentially we do. This is just a tier 1 method to convert the activity data into CO2 emission estimates. Now let's have a look at some of the efforts here at the Energy Data Center to enhance the coherence of energy data for climate agenda. One of the main activities that we do is actually a collaboration that we have with UNFCCC. And that is because both IEA and UNFCCC share the mandate of providing high quality data, which is useful for addressing our climate change and sustainable development goals. And energy is actually obviously in the core of such issues. And the UNFCCC calls for the conventions to the parties to estimate and report their national greenhouse gas inventories to UNFCCC. And we support UNFCCC in their review process by comparing the underlying energy data of the emission submissions by the countries to UNFCCC versus the energy data submitted to IEA. And this is an official stage of the UNFCCC greenhouse gas inventory review process. We do this every year, and the objective is to make energy data more consistent, both at the national and international level. Some of the other efforts that we have, it's the capacity building efforts that we have. We held a joint IEA, UNFCCC, United Nations Environment Program workshop on energy data for climate policy last November. And the main goal and objective was to discuss with experts from developing countries on how to further align the energy data used in the energy sector versus the climate mitigation sector. We have a dedicated page on our website for this workshop, which you can access by clicking on the link. And there are various useful presentations available, which you can easily download and have a look at for free. And hopefully we're actually hoping to hold the physical workshop later this year in December. to further work on this work stream and help the developing countries to further align energy data. And to conclude, I want to again emphasize that today there's a scientific consensus that anthropogenic or human-induced activities have resulted in an increase in the concentration of greenhouse gases in the atmosphere, and as a result, an increase in the global mean surface temperature. This is a global problem, so in order for us to solve it, we need international collaboration. And as we saw, having validated emission estimates are key and essential in order to be able to track our progress and understand what is driving these emission trends. And most importantly, good energy statistics are crucial for estimating these emissions. And the emission estimates are only as good as the energy statistics which underlies them. This is our famous CO2 emissions from fuel combustion publication. Our annual publication with global coverage is typically released around July and has a CO2 emission estimates and related indicators for over 190 countries and regions. However, with an effort to increase the timeliness of our data releases, in the past few recent years, we also have the early release of the data, typically once in February and once in April, with the data of the countries which has been so far validated. In our latest release in February, we published the data for over 35 countries, I think around 39 countries. And some of the data included in this publication can be accessed through our data browser on the website, and also in an Excel format, which can be downloaded for free from our website if you click on the link provided. And if you guys have any questions, you can always address it to our email address written down there. Thank you for listening, and I would be happy to answer if there's any questions now.